Hello everyone. So today we are going to start the sequential circuit, and the topic today is shift register. Now, what is a register? So before starting, we need to define a register. Okay, and it goes like this: registers are digital circuits which are used to store n bits information in the same time, and each bit is stored in a flip-flop. Now, what does it mean? See, flip-flop is basically a 1-bit storage element. We know that it's a 1-bit memory. So if you want to store n-bit memory, or you rather want to have n-bit information in hand, then you need to have a collection of flip-flops. And a collection of flip-flops is basically a register in some way. It's this collection of flip-flop, however, follows suitable logic and structure, which we will be going to discuss in some time. Now, generally registers are built with D flip-flop because that is the most easiest way to store memory. Why? Because in D flip-flop we know that output simply follows the input. So if D is 1, you will store 1. If D is 0, you will store 0. So that is a very easiest way to store any memory in a flip-flop as such. So therefore registers are built with D flip-flop. However, that doesn't mean that we can't use any other flip-flop. Register can also be designed using SR and JK flip-flop, and presently they are available in MSIICs, okay? Medium scale integrations. The register is said to be synchronous device because all the flip-flops change state at the same time. Okay, so it is synchronous in nature. Now let us move to the next state, and that is a buffer register. Okay, so you can see here we will be having a simple register configuration constructed with 4D registers, as you can see here. So this is the logic diagram of a 4-bit buffer register. Okay, this register is also called buffer register. Why? Because each D flip-flop is triggered with a common negative H clock pulse. On the application of clock pulse, the output word becomes the same as the word applied at the input terminal. So we are having here input terminal x0, x1, x2, x3. So whatever you will be going to apply over here, simply it is going to store here, and that's why it is called a buffer register. Here there are 4 flip-flops, and definitely it will be 4 bits. Okay. Therefore, when the first negative clock edge arrives, because you can see here, every flip-flop is driven by the same clock, and all are negative edge triggered because there is a bubble in the clock, so you can always be able to distinguish between a negative edge clock and a positive edge clock or triggering. In this register, 4 D flip-flop are used. Okay, so it can store 4-bit information, binary information. That the number of flip-flop stages in register determines its total storage capacity. So you can have n flip-flops to store n-bit data. Okay. Now shift register. What exactly is a shift register? So as you can see here, a number of flip-flops connected together such that the data may be shifted into and shifted out of them is called a shift register. That means either you can pump in a data, or you can rather take out a data from a collection of flip-flops, which is a flip-flop as we have defined earlier. So in the shift register, the stored data can move from a particular location to some other location within the register. Okay, so the data can rather move from one flip-flop to another upon our wish. In other words, the flip-flops are connected in such a way that the bits of a binary number are entered into the shift register, shifted from one position to another, and finally shifted out. The storage capacity of a shift register equals the total number of bits of digital data it can store, which in turn depends upon the number of flip-flops used to construct the shift register. It's very certain. Since each flip-flop can store 1 bit of data, the storage capacity of the shift register equals the number of flip-flops used. Now the first one is this variety of flip-flop register, and there is a CISO. There is a serial in, serial out shift register. So serial in, serial out. This is how the data will be fed in and fed out. CA. So in this way, data will be first fed as serially. Okay, data will be entered serially, and after the data is entered serially, now one by one the data will be popped out at the output. So it will be serially in and serially out, and it is called a CISO shift register. Now it is illustrated in the above figure that the data inputs in the shift register are serially 1001, and data output from shift register is also serially. Okay. Now serial in, serial out shift register is again divided into serial in, serial out shift left register and serial in, serial out shift right register. That means either you can enter the data left, shifting left, or shifting right. We will talk about in just. Serial in, serial out shift left register. So right now we are concentrating on the shift left, shifting left operation. So a 4-bit left shift register using is shown in figure below, which consists of D flip-flop. So this is how it goes. Okay, as you can see here. Okay, data is entered from left. Okay, from left. Okay, you can see here. So therefore it is a serial in and serial out configuration driven by the same clock. Okay, all are negative triggers. In this shift register, data is entered in serial form and data output is also in serial form, and data moves from right to left. Okay, data moves from right to left. So it is shift left. Okay, so here it is. You can see the data will be shifted left, and here will be the output. Okay. Since it is 4 flip-flop, it can store up to 4 bit of data. Serial data is applied at the D input of the first flip-flop, rightmost flip-flop. As you can see here, this is the D input at the right. Why it is right? Because we want to shift it left. Okay. The Q output of the first flip-flop is connected to the D input of the second flip-flop. Okay. So actually it is talking about the configuration, days and days and days, and this is how it goes. Okay. The Q output of the second flip-flop is connected to the D input of the third flip-flop, and the Q output of the third flip-flop is connected to the D input of the fourth flip-flop, and so on and so forth, if you want to increase the size of the register. The output data is taken from the Q terminal of the last flip-flop. Okay, so this is the output which is taken from the Q terminal of the last flip-flop. At present it is Q3. Now, as you can see here, so initially it is 0 0 0 0. Okay, initially it is 0 0 0 0. That means all the flip-flop present input is 0 0 0 0. What happened? First input is applied over here 1. What will happen when first input is applied over here 1? What will happen? This flip-flop 0, here it will be stored as 1. List all will be 0. Okay. You see, rest all will be 0. In the second clock, so that happens in the first clock, negative is triggered. In the second clock, which is negative is triggered, what will happen? What will happen? Again, because my input is actually 1111. Okay, I want to store 1111. Okay, and it is going left, as you can see here. So in the first clock, I am successfully able to store 1 in the first flip flop. Okay. In the second clock, this one will again store in here Q0 to 1, and as we are using D flip flop, so simply this one, okay, so simply this one will be stored here, okay, because it will see output as 1 over here in second clock, and it will store. And likewise, okay, likewise in the fourth clock, all the flip flop will be able to store 1, or rather the input we have applied. If it is 1011, it will be 1011, and so on. Okay, and this is the direction of the data travel. That is the shift left operation. The data in each stage after each of the 4 shift pulses is shown in the table above, which is shown. Now serial in, serial out, shift right operation register. Now you can see here the same configuration. Just what we have done is we have to change the direction of the data feed and the data taking out serially. So as you can see here, now it is shift right. Now this is a 4-bit serial in, serial out shift right register. The right shift register using D flip flop is shown in the above figure which we have shown. In right shift register, data is entered in serial form and data output is also in serial form. Data moves from left to right. Its operation is similar with left shift register, but only difference is the direction of data movement. In this case, serial data is applied at the D input of the first flip flop, which is the leftmost flip flop. As you can see here, this is the serial port. In previous case, it was here. So because it was shift left, right now we are considering shift right operation. So naturally we are giving the input at this one, and it is moving towards right. Okay. The Q output of the first flip flop is connected to the D input of the second flip flop. The Q output of the second flip flop is connected to the D input of the third flip flop, and the Q output of the third flip flop is connected to the D input of the fourth flip flop. The output data is taken from the Q terminal of the last flip flop. You can see here is the same operation. Negative is triggered, first clock, it sees 1 over here, it enters here. Okay, and with each clock, data is basically stored serially. You see here, serially. First this is stored, then this is stored, then this is stored, then this is stored. Okay, so at the end of the fourth clock pulse, you will be having Q3, Q2, Q1, Q0 as 1, 1, 1, 1. At successive clock, it will store 1, and finally you will get here 1, 1, 1, 1. And this is the direction of data travel. That is a shift right operation. The data is stored after each of the 4 shift pulses shown in the table above. Now let us talk about the serial in parallel out shift register, SIPO. See, the same thing. Data we are entering serially, but data is we are taking out parallelly. So it will be faster compared to the previous case. So serial data input and parallel data output in SISO shift register. Okay. So one thing, this is actually SIPO. Okay, this is serial in parallel out shift register. Okay. Now in SIPO shift register, data bits are entered in shift register serially, and the data bits are taken out of the register in parallel. So as you can see here, data is entered. So you can see here, data is entered. So you can see here, data is basically entered here serially. Okay. Okay. But it is now taken out parallel. So serial in, but parallel route. So that is the difference between the, okay. Now you can see here, this is the data input, okay. This is the data input, okay. Same like serial in serial out configuration, but here instead of taking in the prior case, like in the CISO case, we were taking output from the last output of the last flip-flop or the end flip-flop, whichever you want to say in the register configuration, okay. But here we are taking the output parallelly from all the connections over here, okay. So once the data bit is stored, okay, so once the data bit is stored, each bit appears on its respective output line and all bits are available simultaneously rather than on a bit by bit basis as with the serial input. So in serial input, we have again, like in serial input, we have to give 4 clock to store, suppose 1 1 1 1, okay. But if you want to take out the data, then again we have to apply the clock pulse, okay. So you will get 1 and then again 1 and then again 1 and then and so on, okay. But here in case of the CIPO configuration, if you store 1 1 1 1, straight away it will already be available after the 4th clock pulse, okay. So it is faster definitely. So let us see the timing diagram. So suppose it is a data over here is 0110 data in. This is the clock which goes on. You can see here in the first clock, it will store this one. This is the second clock, third, and finally this fourth. So what will happen? So 0110 is actually our data. You see 0110. So we don't need any other clock. Straight away we are able to get the output here, okay, at the output ends. So that is the advantage compared to CISO. Thank you.